All right, welcome to CS4510, L07B, and this is on something that's called Parikh's theorem. And essentially all it says is like, you know, what's really conceptually the difference between a language like A to the N, B to the N? Is that you have N A's and N B's, but the A's must come before all the B's. What's really the difference between a language like this and A B star, right? This one is A, B, B, B. This one is A, B, right? But they are basically, I mean, like they're totally different languages, but the difference between them is the order that letters appear in the words, right? One of these enforces that A's must come before all B's, and this one just says that they can come where who cares, A, B, right? This one is context-free and not regular. We pumped this one because we had to use to make sure that not only the A's came for all B's, but that exactly N A's came before exactly N B's. Here we just say A, then B, then A, then B, then A, then B, and that can be done very locally where you just make sure you see A, B in that order. So the A's and B's cancel themselves out. And this is a regular language. This is a context-free language, right? So in some sense, this is just a reordering of the strings in this one. So what Parikh's theorem really says is as follows. If you ignore the order of letters in a word, then the context-free languages and regular languages are indistinguishable. So essentially, what is the difference between a regular language and a context-free language? The order of letters in a word. That's really all it is. That's what makes a language context-free, and that's what makes a language. The difference between a regular and a context-free language is only the order of letters in the word. In some sense, they are identical in that sense. So how do we formalize this? How do we talk about some way to ignore order of letters, but still have access to the string? So we want ourselves to not be able to like read the string in a way like left to right, we say A, B, B, A, whatever, but we want to be able to like read the string in such a way that we can't actually determine the order of letters. The only thing then that we can determine is, for example, then the length of the string and the frequency of letters in the string. So we define this like frequency function, which takes strings and maps them to basically vectors, such that it's defined as a tuple of the frequency of appearance of letters in that word. Right? So what this is basically a vector. It's a tuple of integers, of numbers, such that the number here is like how many times does that letter appear in the string, right? So for example, what would be the frequency of, let's consider the string like A, B, A, B, A. Yes. That's basically it. Now, we, in our blindness, do not look at A, B. We look, A, B, A. We don't look at that. If we're blind to reading the order of letters, we would look at this, because this would just simply be the frequency and not like, it wouldn't, if you're looking at this piece of information, you don't know the order of letters. You only know this one. As another example, what about, I don't know, A to the 17, B to the 20, AA.
19, 20?
Yeah. Okay, so we can calculate the specific frequency of specific strings. What about languages? Let L be a language and define the frequency of the language to be vectors that are frequency of the strings. Something like this, right? Just take the vectors of every string in that language, right? So what would, for example, the frequency of A star be? It'd be a set of vectors, right? But which ones? Yeah, basically. But if we were to do the syntax correctly, there would be no b's in any number of a's. So we would say n comma 0 for n is a natural. But basically the naturals. But we got to data structure it up, right? Similarly, what about B star?
Same as above, just flip it.
All right, what about phi of A star B star?
N1, comma N2, where N1, N2 are in the naturals.
Yeah, and they're not necessarily equal. Let's call it IJ. What about A B star?
N, comma N.
Yeah.
Where N is in the naturals.
What about the frequency of A to the N, B to the N, which is that one generated by the context-free language?
It's the same, it's also n comma n.
Exactly. That is basically what we're going to be proving today. Notice that we said the difference between these two is really only the order. Notice that these two have the same frequency, right? That's basically what we're going to prove, is that every context-free language has the same frequency as a regular language. Let's do a little bit more. What about the frequency? We gave a context-free language for this one. Excuse me, context-free grammar. A to the 3n, b to the I, c to the n minus I. Remember we gave the CFG for that one? What would that one be? This is a little difficult to formalize. You could just say ni and n minus I, but I'll rewrite it this way to illustrate something. Let's call this 3i plus j, I, j. I comma j are naturals. Right? What about that language 1 to the n squared?
Zero, comma N, where N are perfect squares.
Exactly, but I'm going to write it like that.
That works.
It's the same thing. The reason I'm writing it like this is I want to illustrate something. This language is not regular. We also know, we didn't prove it, but the proof would be identical. This language is also not context-free. Instead of v to the I, instead of you pump y to the I, here you would pump vy, and then you would get basically the same argument, okay? But really, what's the deal with the ones that look context-free and the ones that look regular and the ones that don't look context-free? Is that if something is not context-free, it might look basically linear, right? And there's a big connection between context-free languages and a whole thing about linear algebra. But I don't want to get too specific into some of that math, but just kind of probably you believe it, right? You can get 3 to the n and then some linear combination of stuff over here for a grammar like this, but you could never do n squared, right? So you can always do like multiples of stuff. So you get linear-like properties. But it's basically, you can characterize the regular and context-free languages by linearness. There's technical words that I'm supposed to use there, but you can just kind of see everything looks like linear functions, right? Now, it's not true that if it is linear, then it must be context-free, because what is the frequency of a to the n, b to the n, c to the n? Yeah. Also, linear stuff, right? Right, there are some properties of the frequency function we would like to use. So one of them is going to be, let not these be languages but words. What is the frequency of W1, W2, where this is a concatenation?
Just add each element of the tuples.
Sure. So what would this be? Let's suppose this is only one word and one word. Express this as something else.
Frequency of W1 plus the frequency of W2?
Precisely. Right? It has, basically this is where the linearness comes from, because the frequency function kind of does linear-like stuff with the concatenation. If you see this, actually one more thing. What is the frequency of the empty string? It depends on what the alphabet size is, but what should it be?
All zeros?
Yeah, it's going to be the 0 vector. Whatever the alphabet happens to be, right? What does this function remind you of? There's a name for it.
Logarithm?
Yes, it is, yes, but the logarithm has a certain property. That is true, yes, okay, that's really good. This is not necessarily multiplication, but concatenation. So a quote-unquote multiplication of the domain is an addition in the codomain. Logarithm does obey that property. But I guess the term I'm looking for is actually homomorphism. You have this as your domain. Here, the operation is concatenation. This is your codomain. Here, the operation is just addition, vector coordinate-wise addition, right? So this property tells you basically it's kind of like a homomorphism if you consider that operation in here and this operation in here, right? So that's kind of where linearness is going to come from. One final kind of property of it. What is let A and B be languages. What is the frequency of A union B? And A and B, again, are languages, not strings. I can expand a little. If W is an L, if A union B, we know that the frequency of W is an element of the frequency of A union B. If W is an A union B, then we know W is an A, or W is in B. So we know that W is in A, or W is in B. So we know then that W is in the frequency of W, excuse me, is in the frequency of A, or the frequency of W is in the frequency of B. Right? So what do we know the frequency of A union B should be?
The frequency of A union the frequency of B.
Takes a second to discover that, but yeah, we also see another property of that, right? By the way, this is still, we're still talking about context-free grammars. I was at the ICPC conference in Orlando, and I was working on this in the lobby, and a guy comes up to me, and I'm trying to figure out some of these properties, and he asked me, is this analysis? He thinks he sees this psi function, and it's like Schrodinger equation stuff or anything. No, we're still talking, and we're still in a very discrete setting, and we're still talking about context-free languages, right? Okay, so now we want to prove, basically, for every context-free language, there is some regular language such that the frequency is the same. That's basically what we want to prove. But we need two little lemmas to go there, right? The first thing we need is a generalized pumping lemma, right? Recall our normal pumping lemma for regular pumping CFLs. It follows from the pigeonhole principle, which is that if parse tree, what is the normal pigeonhole principle? If m pigeons, n holes, and m exceeds n, then some hole has greater than or equal to 2 pigeons, right? So, and if that was the case, we said if parse tree height was greater than or equal to v plus 1, then we observe the following to occur. S produced some, what was it? It was U, then there exists an A, such that S produced in 0 or more steps some U, A, Z. A produced in 0 or more steps, V, A, Y with V, Y not nothing, and that A produced some terminal string X, right? And we observe this because we have the parse tree S to some A, to some A. Okay, right? That's basically how that whole thing played out. And what else did we have? We had that a Vxy was less than or equal to P, right? That's basically how we constructed the pumping lemma. Now, if we want a stronger pumping lemma, does anyone know what the generalized, we'll call it a generalized lemma of the pumping lemma, whatever, I'm not gonna write that. Fine, lemma of the pumping lemma. Okay, does anyone know what the generalized pigeonhole principle is from memory? The pigeonhole principle essentially gives you that some hole has greater than or equal to 2 pigeons. The generalized pigeonhole principle tells you a little bit more about how many pigeons are there. It basically says the same thing, but then that some hole has greater than or equal to the ceiling of m over n pigeons in it. Right? So it not only says that there's a hole with at least 2 pigeons, it says that there's a hole with some more pigeons, right? Like some specific number it can tell you, right? Like let's say you have 11 pigeons and 9 holes. The generalized pigeonhole principle will tell you that there's at least a hole with more than, let's say you have 30 pigeons and 8 holes. The pigeonhole principle will tell you there's a hole with at least 2 pigeons in it. The generalized pigeonhole principle will tell you what's 30 divided by 8 is, and the ceiling of that is going to be 4. Some hole must have 4 pigeons in it, right? It tells you something stronger, right? There's simply too many pigeons, right? The way to think of it is if you were to uniformly distribute them, there's still too many. You would have to put like 3 in each, and then the last ones would have to go in the hole of size 4. They would make a 4th one, right? If you think of it in the worst case. So what does that give us here? So for any k, if parse tree height is greater than or equal to, let's say, some k times v plus 1, right? Then S produces some UAZ, but then A produces some V1AY1, and some A produces some VKAYK, each with the property that V1Y1 is greater than 0, VKYK is greater than 0, and then that A produces this X. And the picture you should think about is our parse tree here looks like this. U, V1, V2, X, Y2, Y1, Z, right? So, and subject to, well here we have S is equal to U, V, X, Y, Z. Here we have S is equal to U, v1 to the vk, x, y1 to yk, z. Oh, my bad. Yk to y1. Okay, do we believe it? What's the difference here? K copies of A appear by the strong pigeonhole principle, and there are K different possible choices of A producing a V and a Y. Maybe V2, Y2 is actually double of V1, Y1, who knows? But different choices here there are K different versions of V1 and Y1 that you could put in here. So you have V1 to VK and then YK to Y1 that go here, right? Do we believe this follows? Now, the way we'll say this is since the parse tree must have height at most kv plus 1, we'll say that this holds for when the length of s is greater than or equal to p to the k, and the similar condition of vxy must be less than or equal to p, we say that the v1 to vk, yk to y1 must be less than or equal to p to the k, for some fixed k, for any k in fact. This is the generalized lemma of the bumping lemma, right? We're not going to use this to prove a language is not context-free by pumping it with this lemma. We're just going to use this in the proof. This is the first detail we need. Okay. Questions on this, though, conceptually? We see that it appears k times, right? So kind of what's going on. If your tree is high enough, some non-terminal must appear so many times. Okay, we need a second detail before we can get into the proof. And the second detail is the fact that we need to somehow, it'll turn out we need to force certain non-terminals to be used. So if U is a set of non-terminals, like let's say U is like, so the non-terminals again are the capitals. Let's say you have some set of them. Let L of U be strings in L which use exactly the non-terminals of U to be produced. Right? So LU is the subset basically of L, of the strings that use exactly the set of non-terminals U. Pop quiz. What is the union of, for each possible subset U of V of LU? For example, if S was the grammar that said, like, let's say X or Y, and then we said X produced A, X, B, or epsilon, and then Y produced B, Y, A, or epsilon, then we would say that L of the set of just X would be what? What strings are produced that use, let's just use S comma X, right? What strings are produced using S and X? Only those non-terminals. Exactly. Okay, what about the strings that are produced only using S? No other non-terminals allowed. Yeah. Oh.
Nothing, because you have no terminals.
What about the string that's produced with S comma Y?
E to the N, A to the N.
Yeah. And what about 1, 2, 3? So we should have 8 subsets. What about any subset containing x and y at the same time? Say sxy. This is a tricky question. I'll tell you the answer is none of them. Because no string can be produced with both x and y at the same time. It either uses s and x or s and y, if a string is produced at all. But it can never use both. First you choose one and then you never go to the other, right? So s of x, y is nothing, xy is nothing, and some of the others, right? So really, the union then of all these would just be what? It'd be nothing, 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 but then it would be a to the n, b to the n, and then b to the n, a to the n, right? So that would be the union. Correspondingly, what should this union of this be? It's going to just be all the accepted strings, right? If a string is produced by a specific subset of non-terminals only, and you just union over all possible subsets of non-terminals, that's just every string back to the original, right? We're going to do it this way to force ourselves to pick a specific u. Now, here's what we're actually going to prove. For each u, we're going to prove that the frequency that there exists finite sets BU, CU, such that the frequency of L of U is equal to the frequency of BU, CU star. What do you know about finite sets? Every finite language, what do you know about it?
It's regular.
It's regular. You know what about the concatenation of regular languages?
Stays regular.
Correct. What about the star of regular languages? Yeah. So if these are finite, this is regular, right? So basically we're showing that this set has its frequency, its letter equivalent, frequency-wise, to some regular language, right? But we want to do L, we don't want to do LU. So why is this okay? Well, the frequency of L is equal to the frequency of the union of all subsets U of U of V of LU, which we know by the union thing we did earlier, is actually equal to the union for all U subsets of V of the frequency of LU, right? But what do we know that is? We know if we can prove this, that's sufficient for us to say that that is equal to the union of U, which is a subset of V, of the frequency of BU, CU star. And what do we know about the union again? We can actually just bring it back in. So we get the frequency of the union of U subset of V of BU, CU star. Right. Now, importantly, this is L. This is, what do you know about this?
It's regular.
Yeah. Finite languages are regular. Star of a language is regular. Concatenation of a language is regular. Finite union of regular languages is regular. So this is in fact a regular language. So what we're going to prove is if L is context free, then this is a regular language that has, by equals, 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 the same frequency as L. So for every context free language, some other regular language exists that has the same frequency. That's what we're going to prove. This is basically the easy part of the proof. All we need to do now is fix U and show this for any possible U. So if we can show that, convince yourself that we've proven the theorem. Questions on that? Okay. So fix U. Let LU be as defined, where it's the strings in L such that it only uses non-terminals of U. Let B be the following. B is going to be, W is an LU such that the length of W is less than or equal to P to the K. And we're going to have C be pairs of strings Vy, which is in sigma star, such that 1 is less than or equal to Vy, which is less than or equal to P to the K. And there exists some A specifically in U such that A with 0 or more steps will produce Vay. Okay? So basically, maybe you can already see what's going to happen. When we star C, we're going to take copies of that, and that's going to basically quote unquote follow from the pumping, right? So now we need to prove that phi of LU is then equal to phi of BU CU star. How should we prove two sets are equal? Yes. Let's proceed with this direction first. How should we proceed by proving a set containment? This is difficult. We want to take W, to prove a set containment, we take an element in here and show it's in here. So we could say something like, let W be an LU, and therefore the frequency of W is in the frequency of LU. We prove by induction on the length of W that the frequency of W will be in the frequency BU CU star. If we can prove that, we've proven our one direction of our double set containment, right? So we proceed by induction on the length of W. Base case, what should our base case be? I don't think anyone's gonna get this, but let's see. What's our base case? In fact, we have a lot of base cases. Just pick a string in B, right? Obviously, just by definition, it's in LU, right? So, it's gonna be in, if it's in here, it's gonna be in here. Base case, let W be an element of LU with the length of W less than or equal to P to the K, right? Notice that by construction, it is simply the case that W is in B, right? That's just the definition of B. So we know then that implies that the frequency of W is in the frequency of B. And that implies then that if you take that 0 or more copies of C, right? So that implies the frequency of W is in the frequency of B, I should put a U here, sorry. Of BU CU star. Okay, done, base case, right? If it's a short enough string, it's just in U. We don't have any C's in there. So it just happens to be in B, right? So what's our induction hypothesis going to be? Well, I'll say, what's our induction step going to be? Let W be an LU with the length of W exceeding, strictly so perhaps, P to the K. Our induction hypothesis is if some W prime has length less than W and the frequency of W prime is in the frequency of LU, then the frequency of W prime is in the frequency of BU CU star. So basically, just pick some long string. That's going to be the step we're at in the induction. And our induction hypothesis by strong induction is just like any string that's shorter, those have the property for us, just by definition, right? That's going to be our induction step. And this is what we're going to try to prove. So let W be some longer string, and let's assume that all shorter strings are in there. Okay. So if W is longer than P to the K, what do we know about W? It really should be greater than or equal to here, and this should actually be less than or equal to, but. I'll tell you, we apply the generalized pumping theorem. We get to say that W is equal to U V1 VK X YK Y1 Z with S produces UAZ with there exists some A in U specifically, that X produces UAZ, A produces V1AY1, A produces VKAYK, and A produces some string Z, some X. Subject to all of those conditions, right? So, if X is this long, we can apply the generalized pumping lemma that we have, and we can see that we could break X up into W up into all these pieces. Fine. But we can then pump down. If we pump down, what I mean by pump down is just forget to apply some specific A goes to VI, AY, right? If you forget to do that, then you're going to say make W prime by pumping down some VI AYI rule, right? Then we can say the frequency of W is equal to the frequency of U V1 X VK X YK Y1 Z. But we know that if we forgot to pump down some VY, if we create W prime by pumping down some VI YI, then this is equal to the frequency of W prime plus what? What's really the difference string-wise between W and W prime? W prime certainly is shorter.
It doesn't include VI and YI.
Correct. Exactly. W prime simply doesn't have VI and YI in it. But if we are considering the frequencies, what can we add here?
The frequency of VI and the frequency of YI.
Correct. Like that. Okay? What do we know about what do we know about W prime? Since the length of W prime is less than the length of W, what must be true?
By the induction hypothesis.
Exactly. By the induction hypothesis, we know that the frequency, since a sequence of productions, we know that since a sequence of productions exists for W prime, which is based upon the sequence of productions for W, we know that W prime must also be in LU. It also uses the same non-terminals. So we know that the frequency of W prime must be an element then of the frequency of BU CU star. Right? So what does that tell us about the frequency of W plus VIYI? What do you know about VIYI, by the way?
It's non-zero, but I'm not sure if that's true.
It is non-zero, but by construction, what is the relationship between VI, YI, and B or C? In fact, C is simply defined to be those things that are from the pumping limit, those VI, YI pairs. So we know that the frequency of W prime is in BU, CU star, and by construction, we know that the frequency of VI, YI must be an element of the frequency of, not even that, we can say that that VI, YI itself is an element of CU. So, the frequency of W is equal to the frequency of W prime VI, YI, which is actually, if that's in BU, CU star, and that's in CU, then the concatenations of those are going to be an element of the frequency of BU, CU star concatenated with CU. All right? Well, whatever that is, that's simply a subset of the frequency of BU, CU star. Right? So, the frequency of W is an element of the frequency of BU, CU star. And we've proven one direction of the containment, right? Pump down, wow, that's just by induction and by construction, it's in the BU, CU star. The CU star is literally the pumping part. Oh, this was in the base case, this was in the pumping part, we're good. Pump back up, you get the same thing, right? Questions on this direction of the proof. And in fact, this is the hard direction. We believe now this should be true, right? That LU, the frequency of LU is a subset of BU, CU star. Okay? What about the reverse direction? We want to prove now that the frequency of BU, CU star for those specific B's and C's is a subset of the frequency of LU. How should we do so? It's going to be, again, a kind of a simple induction, actually. So what are we going to induct upon? Basically, we're going to induct upon the number of stars that are going to happen here. Notice that BU, I don't know if that can be seen. Yeah. BU CU star is actually equal to BU union BU CU union BU CU squared union and so on. So we're going to induct upon the number of times that star would be taken. So base case, we say that we say that W is in the frequency, W is in BU, right? Why is it the case that the frequency of W is in the frequency of LU?
It's defined such that CU is never zero, so if CU is zero, if there's nothing in it, then BU is, by definition,
Yeah,
smaller than.
exactly. Just by definition, BU is explicitly what? It's just the set of strings in U less than something. So in fact, BU is a subset of LU. So if W is in BU, then W is in BU, which is a subset of LU. So trivially, we know from here that W must also be in LU, which implies this, right? The frequency's in there. Okay, done. Now, suppose that if W is, if the frequency of W is in the frequency of BU CU to the K, then the frequency of W is in frequency of LU. We prove that if the frequency of W is an element of BU CU to the K plus 1, then the frequency of W is in the frequency of LU. Okay. That should make it clear at least what we're inducting upon, right? So, in fact, rather than assuming the frequency, just let W be an element of BU CU to the K plus 1. What do you know about W here? Well, inductively, like, there's a BU CU to the K here, and then there's an extra CU, right? So we can say that W is equal to some W prime Vy for W prime in BU CU to the K, right? This is, there's some V portion and there's a C portion, whatever those are. Let W prime just be all that, and let that extra factor be this Vy here, okay? But if W prime is in BU CU to the K, by the induction hypothesis, what do we know about W prime? The frequency of W prime is in fact an element of the frequency of LU, right? We don't know that W prime is in LU, but we know that the frequency of W prime is in LU. So some W double prime exists in LU such that the frequency of W prime is equal to the frequency of W prime prime, right? So W prime may not be in LU, but its frequency is in the frequency of LU. So there is some other thing in LU called W prime prime that is in LU that has the same frequency, whatever that happens to be, right? If W prime exists in LU, we know something about the definition of by the definition of LU, the production of W prime prime uses all non-terminals in U, including A, right? If Vy is in Cu to the K, if Vy we know is in Cu, since Vy is in Cu, then there exists some A such that A produces Vay, and this also only uses the non-terminals U, right? So create W prime 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 by pumping this into W prime prime. What is that going to give us now? We're going to have, what is the frequency of W prime prime? Prime. W prime 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 is created from W prime prime by pumping the Vay into W prime prime, right? So we know that this is equal then to, had we taken W prime prime and then we pumped Vy into it, right? By definition. But by definition, what do you know is equivalent to the frequency of W prime prime? Yes. To simplify, let's just concatenate those two. You may already see what that's going to be. What do you know about W prime Vy?
It's an element of, or frequency is an element of BUC.
Even simpler, it is simply the frequency of W, right? So how does this tell us that, what do we know about the frequency of W? Well, we know that by our induction hypothesis, W prime 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 must be in LU, right? The frequency of it. And if we know that W prime 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 is equal to WU, then QED. Questions on that? Again, what did we do? We split the frequency of the word into its factors. We broke off the last factor. We said by induction, by the induction hypothesis, all of this has the right frequency. Now if we add it back in, guess what? By induction, we get a string of a frequency in the language. So therefore, we're good. QED. Questions on this? I'll give you one lemma of Parikh's theorem. The proof of Parikh's theorem, there are many proofs of Parikh's theorem. They use really different techniques and they're really exotic. There was one I found last night that explicitly constructs a DFA. Given a context-free grammar, you can construct a DFA such that the DFA accepts strings of the same frequency as that the grammar produces. And that proof is a little constructive and a little difficult to actually get. But I'll give you one quick corollary. Let L be some language which is a subset of one star. So L is a unary language, right? If L is context-free, what do we know by Parikh's theorem? Parikh's theorem, rewinding all these details of the proof, what we really said was that every context-free language was letter equivalent to a regular language. Where R here, there is, for every context-free language, there's some other language which is regular, that's letter equivalent to it. Where R was in fact, it was the union of U and V, of B, U, C, U star. Doesn't really matter what that exactly is, but it's regular, and that's all we really care about, right? L is a context-free language is letter equivalent to a regular language. So in the specific case that you know that L is unary, what do you also know about a context-free unary language?
I would say just that it's regular, it feels more complicated.
It is regular. Every unary context-free language is regular. So specifically in the case when sigma is equal to 1, LDFA is equal to LCFT. So really, the context-free languages are like regular languages with order. And that makes kind of a lot of sense based upon language, the way we interact with language, the whole Chomsky thing, right? The precedence and the way that terms appear in sequence is really the major difference between a regular language and a context-free language, right? The other thing is like, if L is a subset of one star and L is not regular, suppose we pump it, what do we know about L as well?
The contrapositive, it's not context-free.
Yeah, then L also isn't context-free. So what do we know about 1 to the n squared?
It's not regular or context-free.
Yeah. We proved it was not regular by the pumping lemma, but because it's not regular and it's unary, We also know it's not context-free. We don't even have to pump it. True of any such languages, right? This only holds if they're unary. But more than the linear algebra, and you could prove Parikh's theorem with talking about something called semi-linear sets, and you could talk about how the mapping of regular and context-free languages both go to this linear algebra-looking thing, where it's just sums and coefficients, and there's no squares in them or any things like that. Rather than talk about that, we can just, more conceptually, it's better to think that really, if you're blind to the position of letters, then these are identical. You cannot tell the difference between these two objects. If you had some sort of monster or a computer or something, an alien that somehow read input not in a way that could determine order position, but only frequency of letters and perhaps length, then it would not know the difference between the regular and context-free languages. It would perhaps lack the ability of language. Any questions? Parikh's theorem? All right, see you.